All right, everyone, welcome to Étale Cohomology on December 3rd, 2020. So today is our last official class. I think my hope is to at least finish sketching the proof of Riemann hypothesis today. We'll see how that goes. And then if that happens, then we'll have one more unofficial class, probably sometime next week. It will not be next Tuesday. There's no class this coming Tuesday. Unfortunately, I haven't figured out my schedule yet because I'm on an NSF panel next week, which is going to take up a lot of time, but I'll make an announcement on the Discord. So before I begin, are there any questions about what we've been talking about recently, or anything course related?
Can you remind me how the subgroup I is constructed of inertia?
Sure. Yeah. So the question. So let's remind ourselves maybe what the general situation was, and then I'll talk a little bit about that question. So the general situation is we have a Lefschetz fibration. And then I'll discuss the relevant properties of the inertia subgroup. So what this was is we had X inside of projective space, a smooth projective variety. We had a line inside of the dual projective space. So this is like a line of hyperplanes, if you'd like, in Pn, such that the base locus of L. So the base locus of L is just the intersection of all the hyperplanes contained in L. So that's a codimension 2 subspace. Intersects X transversely. So that was 1. So 2, xt, which is just X, intercept the hyperplane T, hyperplane indexed by T for some T and L, is smooth for almost all T and L. So almost all means all but finitely many. And 3, for xt singular, xt has a unique singular point, and it's an ordinary double point. Okay, so that means it analytically locally looks, analytically meaning the complete local ring, looks like the cone point of a cone over a non-degenerate quadric. Okay, so this was the situation we were studying, and I claimed that via kind of a Bertini argument, any smooth projective variety, maybe after changing the projective embedding, admits such a Lefschetz pencil. So this is a very general situation. And then we were studying the monodromy of the base. So of the open subset of L where these xt are smooth. So we get this family, which I'll call X, which is the blow up of X, the base locus, to L. So we get this map, which I'll call pi, and the pi inverse of T is xt. Okay, so this is the situation we were studying, and we wanted to understand the monodromy so we wanted to understand the higher push forwards of the constant sheaf through pi. So those are going to be local systems on some open subset of L, or locally constant QL sheaves, if you'd like. And we wanted to understand how pi1 of that open subset acted on them. And so what Ben asked was just to remind us, I gave some local statements about inertia subgroups of pi1, and Ben wanted me to remind you guys what those are. And so let me do that. So what's the situation? So if we let let's let S inside of L be the set of points such that xt is singular, the set of points T such that xt is singular. And then we get these sheaves Ri pi lower star of the constant sheaf QL restricted. If we restrict these sheaves to L minus S, these are locally constant QL sheaves. And so they correspond to some representations of pi1 Étale of L minus S into GLN QL. Okay, and we wanted to understand these representations. And then the observation was this group pi1 of L minus S contains some kind of special subgroups, which are well-defined up to conjugacy. So those were called the inertia subgroups. So let me answer Ben's question now. So for each S and S, you get an inclusion. You can take the kind of complete local ring of P1, so L is a copy of P1 at S, and take its fraction field, right? So you can take the inclusion of spec of the fraction field of O L comma S into pi1, sorry, into L minus S. Right, and if you're over an algebraically closed field, pi1 of this thing is just pi1 of this fraction field, respect of this fraction field is just the inertia group. So over an algebraically closed field, so let's just base change to k bar. So then we get a map. So base changing to k bar. So we start maybe over a finite field, but we're always going to be working with geometric fundamental groups. So we'll base change to k bar. So we get a map pi1 Étale of spec of the fraction field of O L k bar comma S. And this goes to pi1 Étale of L minus S k bar. Okay, and this group here is what's called k bar, or sorry, it's what's called IS, the inertia group at S. Okay, okay, this is pi1 of a field, so it's actually a very concrete object. It's just the absolute Galois group of this field. Okay, and what is this field? It's also pretty concrete. So this field, frac OL k bar S. So when I write this, I actually mean, maybe I should say it doesn't really matter, but let me make things simpler and say the complete local ring. So what is this field? This field is just k bar double bracket, double parentheses T. So if you'd like, the inertia group is just the absolute Galois group of that field. But it's a subgroup of pi1 because there's a map from that field into your ring. Does that answer your question, Ben?
Yeah, I was more wondering like what it means geometrically. Like, is it?
Oh, I see. Yeah. So there's a very natural picture. So you're supposed to think of this as like a punctured disk, and this L minus S is just P1 minus a bunch of points. So what these inertia groups are is you're supposed to think they're generated by very small loops around punctures.
Right. So are they like they're the subgroup of the pi1s that are only defined on that are ramified around S, something like that?
That's right. Yeah. So it's the,
like if you added the points back in S, you'd lose as automorphisms or something.
That's exactly right. Yeah. I mean, it's a little subtle. It's not exactly. I mean, it's not a normal subgroup, right? So it's not. If you add those points back in, you get a map from L minus S to L minus a smaller set, so a bigger open subset of P1, and it's not the kernel of that map. The kernel of that map is a normal subgroup, but it generates the kernel of that map normally. Okay, and oh, sorry.
Why don't we use that group instead?
It's too big. We don't understand it.
Okay.
Yeah, yeah, and so these groups are not well defined. They're only well defined up to conjugacy, and the reason why that is because I've omitted base points here, right? So really, you only get a map like this if you kind of pick a base point, which is a geometric point living over this k double parentheses t point. But if we start with some random base point, that'll move things around up to some inner conjugacy. Okay, but the point is like, okay, so you asked like, why don't we use those bigger groups, like the groups normally generated by these? Well, it's because we know what this group is. Like if K is a field of characteristic 0, this is just Z hat. Or it's like the absolute, like finite extensions of this are just given by extracting roots of T. And characteristic P things are a little more complicated, but we still understand them. But we still understand what's going on. But the group normally generated by it is much bigger. It's very complicated. Does that help, Ben? Mm-hmm. Great. Okay, so last time I listed a huge collection of properties of these sheaves over here. I mean, in particular, the interesting situation is where I is kind of half the dimension of X or one more than that. But I wanna kind of give an example to kind of illustrate what's actually going on, because I think, you know, I just listed a huge collection of properties for you, and I wanna just kind of investigate some explicit situation. So the explicit situation we're going to look at is we're going to look at the family of elliptic curves y squared equals x times x minus 1. Sorry, x minus 1 times x minus lambda. So this is an affine model. So this is a family of elliptic curves, which I'll call E, and it maps to the affine line, and it has singular fibers at 0 and 1. Right, so this is called the Lambda family of elliptic curves. This is an example of a Lefschetz pencil. So here, the coordinate on A1 is lambda. So given you look at the solutions to this, but this really lives in some weighted projective space. I'm gonna just write down the affine model to avoid being super complicated, and you send the fiber over lambda is this elliptic curve. So is it clear what this family is supposed to what this example like means? Does anyone have any questions about it? Okay, so what are the fibers over 0 and 1? So the fibers, I mean, I wrote this over, like, this equation still makes sense at 0 and 1. It's just only smooth. So maybe I'll write it this way. So it lives over A1 lambda, and it's smooth over A1 lambda minus 0, 1. So the fibers over 0 and 1 are nodal elliptic curves. So they're nodal cubics. Right, so for example, when lambda is 0, you get y squared equals x squared times x minus 1, which is like the classic example of a nodal cubic. So I want to understand what the monodromy of this family is. So let's just work over C to try to understand the picture a little bit. So what is pi 1, just the usual topological pi 1 of the affine line minus 0 and 1? Can anyone tell me?
Is it free on 2 generators?
Yeah, so it's free on 2 generators. It's free on, so let me write it this way. It's free on a loop around 0 and a loop around 1. So let me draw the picture. So this is A1, it's the complex plane. And then I'm going to remove 0 and 1. So this is 0 and this is 1. And then if you have some base point, it's generated by some loop around 0 and some loop around 1. Okay. Now, I mean, what I want to do is I want to compute the representation. So if we take R1 pylor star of, let's say, let me just say QL, but you could even, over the complex numbers, you could just take Z, right? So you're allowed to take singular cohomology over the complex numbers, and you could do that here. So this is a local system, or maybe let me write it this way. It's a locally constant QL sheaf on the affine line minus 0, 1 by the smooth and proper base change theorem. So just because the fibers are, I mean, the map is a smooth proper map over this open subvariety of A1. And so the question is so it corresponds to some pi1 representation. So it corresponds to some representation into GL2 of QL. So these are elliptic curves. So their middle cohomology is two-dimensional. So does anyone actually, off the top of your head, do you know what representation this is? It's okay if not. I mean, I was just curious. Yeah. So here's what the representation is. So what it is. I mean, one has to choose bases appropriately and orient these loops appropriately, but you can do an analytic computation. So for example, like I've actually done this with the Weierstrass P function. It's a little harder to do this computation algebraically, but one could also do it, although it would be kind of involved. So what you get is the following representation. So you get gamma 0 goes to the matrix 1, 2, 0, 1, and gamma 1 goes to the matrix 1, 0, 2, 1. Okay. So a couple things to note. So these matrices, and thus the entire representation, is trivial mod 2. Does anyone see why that's the case, actually? So why, if you reduce these matrices mod 2, you'll get the identity? So it actually follows. That's somehow not so hard to see from the form of the equation. So what are the two torsion points on this elliptic curve? So the two torsion points on an elliptic curve, which is written in Weierstrass form like this, are just the ramification points over P1, right? So that's where y is 0 and x is 0, 1, or lambda, or infinity. And so here, the pi1 of this space doesn't shuffle these factors around. Like there's a two torsion section where you send lambda to, for example, 0, comma lambda, or 0, comma 1, or 0, comma 0. So that what that tells you is that this representation has to act trivially on the two torsion of the elliptic curve, which if you translate it, like what that means cohomologically, it means that this representation is trivial mod 2. Okay. So let's try to understand what's actually happening here. So the picture in a neighborhood, let's look in a neighborhood of 0. So nearby 0, what you get, well, nearby 0, you're not actually at 0, so you get a smooth elliptic curve. You get a smooth elliptic curve. Sorry, I don't know why it's not. You get a smooth elliptic curve, which looks like something like this. And then, so this is kind of at epsilon. And then as you go to 0, you get a singular, a nodal cubic, which looks something like this. Right. So there's a loop here that shrinks down to a node. Okay, and what's what is it, what this is an analytic computation you have to do. It's not totally obvious. So what this monodromy matrix is, it says that as you go in a loop around zero, what's happening is you're doing a Dane twist around this loop. So what that means is you're cutting this how should I say this? You're cutting this this torus along this loop and then rotating 360 degrees and then gluing it back. So for example, well, actually, in this case, it's saying you're doing this, you're going 720 degrees. So you're doing that twice. That's what this 2 means. So for example, what happens to the other homology class? So somehow this homology class is being fixed by this matrix. So that's this 1, 0 column. So what's happening to the other homology class? So the let me draw it. So as you go in a loop around 0, oops. So as you go in a loop around 0, what does this other homology class look like? It's just this loop, right? And what is it sent to? Oops. So it's sent to the following loop. So what you do is you start here, and then you turn right and go around twice, and then you come back. So geometrically, this is what this picture means. It means you've taken this loop and you've added 2 copies of the blue loop to it, and geometrically you can represent that by this by this. Sorry, let me. More of this should be filled in than I did. Yeah, so it's like this. You can represent it by this kind of twice twisted red loop. Okay, so this is somehow the picture of this local monodromy. Are there any questions about this? What all this what all these mystical pictures mean? Okay, so let's keep going then.
So in this case, what are the inertia groups?
Yeah, so the inertia groups are the groups generated, well, they're not well defined, they're only well defined up to conjugacy, but it's the groups generated by gamma 0 and the group generated by gamma 1. So they're both copies of Z or Z hat, depending on whether you're in the complex or Étale setting. Right. And so this is what this is saying, this is saying what are those inertia groups doing? They're taking a cycle which is not a vanishing cycle, so a cycle which is not going to 0 here, so that's this red loop, and they're adding to it some multiple of the dual loop. That's the picture. So this blue loop is kind of the dual loop, meaning the intersection of the 2 is 1. So, or if you'd like, the cup product of the 2 corresponding cohomology classes. Well, I mean, these are really homology classes, but you can view them as cohomology classes using Poincare duality. So it's saying the cup product of these homology classes is 1. All right. Are there any other questions about this picture? Okay, so we call this blue loop here, and I've already used this term. Let me use blue. So here we call this blue loop, we call this the vanishing cycle. And why is that? Well, it's because as you go to 0, it literally vanishes. Like it's 0 in the homology here. Okay, so let me now recall the sort of more general situation, and I want you to kind of keep this example in mind, and we'll as I sort of recall the claims we made last time, we'll kind of talk through them in this example, and then we'll oh yeah. So the other, maybe before I do that, the other thing I wanted to note is that that these groups, these 2 elements, they topologically generate, right, an open subgroup of SL2 QL. So if L is 2, it's not the whole SL2 QL, or sorry, SL2, it's not the whole SL2 ZL if L is 2. Otherwise, it is all of, actually, it generates all of SL2 ZL topologically. So it generates a dense subgroup of that. All right. Are there any questions about that before I sort of start recalling the general situation? And then, so I'm going to recall a bunch of facts that we mentioned last time, and then excuse me, and then I will we'll continue with the proof of the Riemann hypothesis, but I'll kind of discuss. I want to discuss the facts that we listed last time in the context of this example. All right, so if there are no questions, let me. Can
you write down what the pairing is on this representation?
Sure. So what it is it's just the pairing. So the pairing is just this matrix. So meaning so what are the two basis elements are these two loops, the red loop and the blue loop. They cup together to give you one. Sorry, this should be a -1 here. They cup together to give you 1 or -1 depending on which order you do it in, and each of them cups with itself to give 0. Does that help, Ben?
Yeah. Great.
Yeah. So maybe it's worth noting. Yeah. Maybe before I continue. So the remark is that the properties of these representations depend a lot on they depend on the parity of the cohomological degree. So if you have if you're an odd cohomological degree, so for example, you're looking at the middle cohomology of a family of odd dimensional varieties, then this pairing is symplectic. So that you don't really see that so much in this two-dimensional case, because the symplectic group is just the same as SL2. I guess you could kind of see it if you looked at other examples, but in even degree you get things that look kind of orthogonal. So for example, so the sort of other example to keep in mind is if you think about quadric surfaces. So if you think about like x squared plus y squared plus I guess t z squared. Wait, is this no, sorry, that would be a curve, plus z squared plus tw squared equals 0. So going to kind of p1t. So what does this family look like? So this family looks like, you know, kind of the generic fiber looks like is like a nice smooth quadric surface like this. And it's kind of degenerating to a quadric cone. So these are surfaces. The interesting cohomology is happening in degree 2. And if you think about it here, you'll see actually that the instead of kind of things like this, these are called transvections. What you'll actually get in this kind of situation is so the inertia will have via reflections. On H2. And this is an example that's actually kind of easy to compute, and you should try it as an exercise. So the point is that the cohomology, the middle cohomology of a quadric is generated by the rulings, right? It's generated by the two lines. So if you have a quadric surface, its middle cohomology is two-dimensional. And then you should think about, well, what happens when you travel in a circle around t equals 0, you're exchanging the lines. So that's the reflection on H2. So that it's just the matrix 0, 1, 1, 0. So meaning so pi 1 of this is smooth away from 0 and infinity. So you look at pi 1 of A1 minus the origin. This is Z, and the generator acts on H2 of x epsilon Z via the matrix 0, 1, 1, 0. So it's fun to work this out. I mean, this is something you really should try to get a handle on these things. So what I wanted to point out is, I mean, so here we're looking at an H1. So here we're looking at R1 pi lower star. Here we're looking at an H2 or R2 pi lower star, and the representations look quite different. And that's not an accident. I mean, that's a sort of typical situation. So for us, when we're proving the Riemann hypothesis, or when Deligne proves the Riemann hypothesis, he uses some special properties of the symplectic group, and that's why we did all this rigmarole earlier on to reduce to the case of even dimensional varieties, so namely Lefschetz fibrations with odd dimensional fibers to get into that symplectic setting. Okay, so let me recall the situation, and then so here let's discuss about these claims about Lefschetz fibrations with odd dimensional fibers. Okay, so last chance to ask questions about these examples before we get into the weeds. Okay, so here the odd dimensional fibers. Let's say, so here let's actually give the name. So let's give it fiber dimension n, which is 2m plus 1. So claim 1 was that for r not equal to n or n plus 1, these sheaves RR pi lower star QL are locally constant on the L, the base of our Lefschetz fibration. Okay, so let's look at in our example. So when n is here, n is 1. So this is saying for r not equal to 1 or 2, this is locally constant, and then it need not be locally constant for n is 1 or 2. Okay, so that's just r is 0, and here, well, in our example, if you take the push forward, r0 pi lower star of QL, you just get the constant sheaf QL because all of these fibers are geometrically connected. Okay, so in our example, actually, it's slightly misleading because r2 pi lower star QL is also constant because all of the fibers have one-dimensional H2, right? All the fibers are irreducible. But you can see that sort of need not happen. So if I wrote down a more complicated example of a family of curves, the singular fibers, well, in fact, for Lefschetz fibration, that this will always happen. Our 2 pi lower star, our Lefschetz fibration of curves, our 2 pi lower star of, sorry, that's not quite true. Sorry, so the example you should keep in mind for where our 2 pi lower star could be not locally constant is if you have something like, this. So this could degenerate to a union of 2 elliptic curves, and then this H2 of this is 2-dimensional, whereas H2 of this is 1-dimensional. So that tells you why you need this n plus 1 here. Okay, but what is this saying? It's saying that these vanishing cycles, so these things that are disappearing in the cohomology, that are making the cohomology change, only show up in sort of middle cohomological degree. Okay, and in fact, maybe it's worth noting, like that's topologically not so surprising, maybe. So one way you can think about this loop is you can think about if you imagine you're looking at the total space of this fibration over a disk over 0, that deformation retracts onto the central fiber. You can just kind of flow it towards the central fiber. And if you take the pre-image of the node under that map, what you'll get is the intersection with one of the fibers will just be an annulus, so it'll be some kind of representative of this loop. So that's called the Milner fiber, and that will always be a bouquet of spheres, or in fact, it will always be a sphere in this setting. And so the point is somehow that those spheres only have interesting cohomology in the middle degree. That's sort of where this fact comes from. And in fact, you can do that you can even make that construction algebraically. So the sort of algebraic avatar of that sphere is sort of the fraction field of the cone over a quadric. Sorry, the cone point of a cone over a quadric. All right. So 2 is that if you take Rn pi lower star QL and you restrict it to L minus the set of bad points, this is locally constant and tame. So tameness just means that the representations of the inertia groups factor through tame inertia. So they factor through z hat. And you can kind of see, I mean, here this example was in characteristic 0, but you can kind of see why that ought to be true. Like that this representation has a abelian image. Great. And then local constancy just follows from the smooth and proper base change theorem. That's not really anything special about Lefschetz fibrations, except for smoothness and properness of the fibers. So let's talk about the vanishing cycles now. So for S and S, there's this co-specialization map from Hn of XS QL to Hn of the generic fiber, geometric generic fiber, QL, and the co-kernel is going to be given by QL of m minus n to 0. Okay, so this map here you should think of as so in the picture, what is this? This is the map from the cohomology of this torus to the cohomology of this loop. So namely, if you have a cohomology class on this torus, you get a cohomology class on the circle by just restriction. So another way of saying that is that this is going to be cupping with a class which we call delta S. So what is delta S? So here delta S is in Hn of x eta QL dual. Well, that's just the same as Hn of x eta bar. Let's see, I think it's just QL of m. Is that right? QL of m or QL of n? Yeah, it's QL of m. Sorry, it's a map from, sorry. So delta S is in this, twisted by m minus n. Yeah, sorry about that. So that's just the image of 1 under the dual of this map. So what is this QL, this dual vector space is just by Poincare duality, this is x eta bar QL of n, the fiber dimension, twisted by m minus n. So where does this live? This lives in Hn of x eta bar QL of m, because n plus m minus n is m. So what is this? This is the image of 1 under the natural map QL to Hn x eta bar QL of m, which is dual to cupping with delta S. Okay, so this is just unwinding how cup products behave under Poincare duality. But the point I want to make is that there's sort of a concrete way to understand. So the concrete way to get your hands on this. So the concrete way to understand the span of delta S is it's the kernel of the dual of the co-specialization map, which goes from Hn x eta bar QL of m dual to HNXS QL of M dual. Sorry, I kind of ran out of space there. Right. So okay. So what is this saying? So what this is saying is you should think of this dual space as some kind of homology. So the dual of the co-specialization map is the map from the homology of the general fiber of your family to the homology of your special fiber, and the kernel is the cycles that vanish when you do that. So that's why these are called vanishing cycles. So that's why this is called vanishing cycles. So in fact, I mean, there's a better way to understand vanishing cycles. So there's a way of understanding vanishing cycles for kind of general sheaves, rather than just like you can understand these sort of upstairs on this family rather than downstairs on the base. And if you do that, what you would get is you'd get a sheaf of vanishing cycles, which is a skyscraper sheaf concentrated at this point. And that's sort of the correct way to do things, but it would be another several lectures. So we can't, unfortunately. Okay, so this is the description. So the sequence is short exact. And what you're supposed to think of it again is you take this co-specialization map. So that's the map from the cohomology of the central fiber to the cohomology of the general fiber. And then cupping with this vanishing cycle is what gives you the kind of co-kernel of that map. And yeah, so pictorially what this is supposed to be is there's a map from the cohomology of this to the cohomology of this, just given by dualizing kind of the specialization map on homology. And then this cupping with the vanishing cycle, giving you a map to a one-dimensional vector space, is just restricting the cohomology of this general fiber to the cohomology of this loop. So that's the picture you should have in your mind. Okay, now we can describe the inertia action. So given an element sigma s in the inertia group at S, so let me just remind you, this was like the Galois group of a Laurent series field. So how does this act? So this acts on a cohomology class X in the middle cohomology of the generic fiber via sigma s of x is going to be x plus or minus something called t of sigma s, x cup delta s times delta s. Okay, so what is this t? So here this t is the natural map. So this t is the natural map from the inertia group at S to ZL of 1. And now that we kind of have talked a little bit about inertia groups, I can say more or less explicitly what this map is. So if in a field over a field, let's just imagine we're over a field of characteristic 0 for a second, even though we're not. So this IS is the absolute Galois group of a Laurent series field. That's just given by extracting roots. All extensions of the Laurent series field, finite extensions, are given by extracting roots of t, right? So the Galois group is given by sending t to t times a root of unity, and if you take the inverse limit of those, you get z hat of 1, the inverse limit of the roots of unity. And so this is just the projection from z hat of 1 to ZL of 1 in characteristic 0. In characteristic P, you just do literally the same thing, except instead of saying all extensions, you just look at tame extensions. And then tame inertia is a quotient of inertia. Okay, so in our picture from before, what does this correspond to? So this corresponds to this picture here, or in other words, to these matrices. So what are we saying? We're saying take a loop, look how it intersects the vanishing cycle. That's the cut product here. And then we add or subtract from our given loop the vanishing cycle times some number, which is determined by that intersection. All right. Are there any questions about that? I'm sorry, so I missed, I see Jose asked a question about that example earlier. So the image in SL2 is gamma of 2. Yeah, I believe that's right. I would have to check. It certainly is contained in gamma of 2 and is finite index. I'm not 100% if it's actually all of gamma 2. I would have to check. Yeah, that's a good question, Jose. I think maybe it doesn't contain -1, 0, 0, -1. So I think it's not quite all of gamma of 2. Okay. Are there any questions about this? So this formula here it has a name. It's called the Picard-Lefschetz formula. Okay, so this is all the stuff I claimed about vanishing cycle, about Lefschetz fibrations last time. So hopefully this example of the lambda family of elliptic curves was clarifying there. Okay, so we're about to get back to the proof of the Riemann hypothesis. So maybe this is a good time to take a 3-minute break. So does anyone have any questions before we take a 3-minute break?
How does I act on the homology?
I mean, this is somehow the formula for it.
No, I mean just like abstractly.
Oh, I see. So I is a subgroup of pi1, right? And so this is a fiber of Rn pi lower star QL, which is a local system. So
Okay.
so a local system is a pi1 rep, and then if you have a subgroup of a rep, you get a rep. Does that answer the question?
Mm-hmm.
Great. Any other questions before we take a 3-minute break? All right, then I will be back in 1 to 3 minutes. All right, I'm back. I mean, we'll still continue. I guess we've 1 or 2 more minutes in our break. Are there any questions you guys want to discuss informally during that time? So okay, so maybe I did want to mention one thing that I think is a little bit illuminating here. So this is, if you're on break, that's okay. This is not super important. So this X cup delta S, so this intersection number of our 2 cycles or 2 cohomology classes, tells us the coefficient of delta S, right? In here, so that's actually this 2 in our picture. So that actually tells us something interesting. So it tells us that the distinguished element inside of the vanishing cycles in this example is not this loop, it's twice this loop. And that sort of corresponds to the fact that we're on the lambda line mapping to M11 is not it's not an isomorphism. It's a finite cover, and it's ramified of degree 2 over both 0 and 1. So I think this example is extremely interesting, and it's worth becoming like extremely good friends with it. And Jose asks, can I at some point repeat the roadmap to the proof of RH? Yeah, so we're going to get back to that in a little bit. Yeah, so maybe our break is over now. So let me now say what we're going to do. So we've now described some kind of interesting classes inside of this middle cohomology. So inside of here, or really inside of this twisted by M. So that's the space of vanishing cycles. And what we're going to do is we're going to try to understand. So when we want to prove, so the idea of the proof of RH. So the proof of RH is we want to understand Hn+1, so this is the middle cohomology of X, the total space of our Lefschetz fibration. So we want to understand the Frobenius action on this, and what we're going to do is we're going to compute it with the Leray spectral sequence. So the interesting part is going to be H1 of P1 with coefficients in Rn pi lower star QL. And this is sort of what we've been trying to understand, this Rn pi lower star QL. So this is something we'll understand via vanishing cycles. So we need to, before we continue, we need to understand this sheaf better. So in particular, we're going to understand the subspace generated by vanishing cycles, and we'll be able to apply the main lemma to that, and then we'll relate to a quotient of that, and then we'll filter it into pieces we understand. So that will be the interesting piece. The other pieces will be simple, and then there's two other contributions to this group. One is H0 of P1 with coefficients in Rn+1 pi lower star QL. The other one is H2 of P1 with coefficients in Rn-1 pi lower star QL. And those will be sort of easy to understand via the induction hypothesis and the Lefschetz hyperplane theorem. Does that help, Jose? So now we want to understand. So our goal now is to understand the monodromy action, so the pi1 action on the span of vanishing cycles. Which live in Hn of x eta bar QL twisted by M. All right. So this will be somehow this is going to be somehow the interesting piece of the pi1 representation associated to this sheaf. Okay. So I'm going to let E. So I'm going to let E subset Hn x eta bar QL be the span of the vanishing cycles. Okay, so there's a little bit of something. There's a little bit of something funny here. So the vanishing cycles live in Hx eta bar QL of M. So because eta bar is an algebraically closed field, QL of M is just the same as QL. So well, I mean, once you choose a generator of QL of M. So the vanishing cycles themselves are no longer well defined in here, but their span is still well defined, because if you change the generator of QL of M, you just multiply everything by a constant. So we're going to understand this span of vanishing cycles. So the proposition is that E is stable under the action of pi1, and the orthogonal complement to E under the cup product pairing coming from the Poincare duality is precisely the part of Hn x eta bar QL fixed by pi1. Okay. let's prove it. So any thoughts? Does anyone see how to prove this? We actually have all the tools to prove this now. At least if you buy the sort of general claims I've made about Lefschetz fibrations, hopefully maybe persuaded by this example of the lambda family. Yeah, so Jose says to use Picard Lefschetz. That's exactly right. So let's check. So what we need to show is that well, first the first observation is to note that the IS, S and S generate pi1 of Étale of L minus S. Well, there's a little subtlety here. So really one needs to put tame here, but for the purposes of this, yeah. So maybe let me make a couple remarks on this. So I haven't told you what the tame pi1 is, but the simplest thing to say is that Picard Lefschetz tells you that this representation factors through a pro-L group. So why is that? Well, it's because these automorphisms are maybe let me omit this issue. So the point is that there's some notion of a tame fundamental group, which is a quotient of the fundamental group, and so this generation follows by comparison to characteristic zeros. This is because the IS generate pi1 of P1 minus S in characteristic zero. So here we're actually using this part 2 here, where I said these representations are tame, meaning the inertia action factors through the tame inertia. Yeah, so there's a little bit of subtlety here, but this is actually a step which really requires lifting to characteristic zero. Okay, so what this means, if you buy this step, is it's enough to show that to show that E is stable under pi1, it's enough to show that IS of delta S prime is contained in E. Okay, but this is immediate from Picard Lefschetz. So if you take sigma S of delta S, what happens? It goes to delta S prime. It goes to delta S prime plus or minus T of sigma S, delta S prime cup delta S times delta S. Well, this is in the span of delta S prime and delta S, so this is in E. All right, so we win. So we've now shown that E is stable under pi1 LS. So now what about so now what about E perp? So now E perp. So yeah, let's see what happens. So suppose X is in E perp. Well, then so that means that cupping with any element of E gives you 0, right? So that means that sigma S of X is equal to X plus or minus, well, T sigma S, X cup delta S, but this is 0 because X was in E perp. So that tells you that E perp is contained in, it's contained, so this implies that E perp is contained in the pi1 invariance. Okay, and then the other direction is actually just the same argument. So the other direction is just the same argument. I mean, this step was an if and only if. So suppose you're in H1 x eta bar suppose you're in the fixed locus. Well, that means that sigma S of X is X, which means that, well, this is never 0, and then so that means that this is 0, which says that you're orthogonal to every one of the vanishing cycles, which means you're in E, which is exactly what it means to be an E perp. Okay, so we now have a subrepresentation, and then we have another subrepresentation, which is just the invariance, which so we've started to understand this representation in terms of the vanishing cycles. Okay, so now we're going to start understanding these. So our idea, sorry, let me maybe write the idea. We're going to start using to prove the Riemann hypothesis is to study the following filtration of this middle cohomology. So we're going to study E intersect E perp. So this is now a constant representation. So this is going to live inside of E, and then this is going to live inside of Hn x eta bar QL. Okay, and so what's happening? So this local system here is not interesting. It's a constant local system on P1. We can understand it just by understanding the fibers, which is something we can understand via the induction hypothesis. So this last conclusion. So let's look at these three parts. So E intersect E perp is constant. So that will be easy to understand. Then there's another part, which is Hn x eta bar QL mod E. This is also constant. Again, by Picard Lefschetz. So why is that? Well, I mean, let's just look at the formula again. So how is some element of inertia acting on an element of this group? Well, it takes that element and then adds something in E. So if you mod out by E, the action is trivial. So this action is constant here. And so then the interesting part. So the interesting part is if we take E mod E intersect E perp. So the vanishing cycles modulo the part of their orthogonal complement that's in their span. So this is going to be interesting. So to understand this part, we're going to need the main lemma. Okay, so in order to apply the main lemma, we're going to have to check that this group, this a priori very complicated group, actually satisfies the hypotheses of the main lemma, right? So what were those hypotheses? Well, it has to have a let's see. So what are the hypotheses of the main lemma? So hypothesis one is that the characteristic polynomial is characteristic polynomials are rational. So let's write this down. So proposition. So the characteristic polynomials of Frobenius on E mod E intersection E perp are rational. So characteristic two is that there's a non-degenerate pairing, symmetric pairing. E mod E intersect E perp cross E mod E intersect E perp to QL of minus n. So that part will be easy. And then three is that the image of pi one, so let's call this pairing C, image of pi one, here, this is pi one of L minus S in SP of E mod E intersect E perp, C is open. Okay, so let's start proving this. So one is non-trivial, but I'm going to skip it. So more or less it boils down to understanding how Galois acts on vanishing cycles. So it's actually not that bad. Like it'll be roots of unity times the power of Q, and then one has to keep track of the roots of unity to make sure that you get something rational rather than just something algebraic. And that's a local computation. Like that boils down to understanding just the Galois action on the cohomology of a degenerating quadric, right? That, I mean, somehow that's the point of Lefschetz fibrations, is that you can reduce to that local computation. But it's sort of very intricate, so I'm not going to do it. So two is not so bad. So two is you just inherit. So the pairing is inherited from the cut product. Okay, so can anyone tell me why it's non-degenerate? So simplex skew symmetric just follows from the fact that the cut product itself is skew symmetric on autodegree cohomology. So why is it non-degenerate? Well, it's because we mod it out by the orthogonal complement, right? So we just made it non-degenerate. Okay, so that wasn't so bad. Okay, so 3 is the interesting part. So step 1 is to show that E mod E intersect E perp is absolutely simple as a pi1 representation. Okay, so this will follow more or less immediately from the Picard-Lefschetz formula and the fact that vanishing cycles are all conjugate to each other. And then part 2 will follow from a theorem of Kazhdan and Margulis, which is that that once you've shown this, I mean, this is more or less going to be yeah, how should I say this? So let me write it down carefully. So suppose that C is a non-degenerate symplectic form. Symplectic form on a vector space W. And G is a closed subgroup of SP of WC. With the following properties. W is a simple G module. Sorry, let me write absolutely simple. Absolutely simple just means that when you base change to the algebraic closure, it stays simple. And B, G is generated by transvections. So what that means is sending X to X plus or minus C of X delta delta. So this should look very familiar. So then G contains an open subgroup of SP. Okay, so how does the proof of 3 go? Well, 1 implies part A here. B is just the Picard-Lefschetz formula in our setting. And then, okay, and now the conclusion is what we're trying to prove, that we have an open subgroup. Okay, so let me just say a word about the proof of 2, since we're almost out of time. So the proof of this Kazhdan Margulis theorem, proof idea for Kazhdan Margulis. So the idea is to use some Elliptic Lie theory. So step A is that it's enough to show. Well, so first of all, I guess step 0 kind of is that G is an Elliptic Lie subgroup. So this is an analog of the theorem over the real numbers, that if you have like a closed subgroup of a Lie group, it's a Lie subgroup. And this is also true elliptically. It's actually much easier elliptically. So once you know this, it's enough to show that the Lie algebra of G is equal to the Lie algebra of SPWC. So this is just because there's an L-adic exponential. So if you contain the Lie algebra, then exponentiating, you get an open subgroup. Okay, and now see, so the transvections imply, so the being generated by transvections implies that the Lie algebra of G, just by taking logarithms, is generated by x plus or minus c. Sorry, is generated by x goes to plus or minus c x delta delta. So this is just what you get when you take logarithms here. And okay, now it's a linear algebra lemma to show that if you have a simple representation of a Lie algebra which is generated like this, then it has to be all of SP. So step D is sort of non-trivial, but more or less elementary linear algebra. All right, so we're out of time. So this is as much as I'm going to check of the hypotheses of the main lemma for E, but the bottom line is that E mod E intersect E perp satisfies the hypotheses of the main lemma. So depending on interest, we'll have at least one more unofficial class where I'll kind of put it all together and explain, I'll just run through sort of the idea of the rest of the proof, how we're actually going to apply this, and then I'll also do 1 or 2 applications. So please request applications in the Discord, and I'll decide what to put in the lecture. Like, I'd like this to be motivated by what you guys are interested in. Then, well, keep your eyes peeled for announcement for the final class, which it might be as early as next Thursday. I just have to figure out what works best for everyone. All right, well, thank you guys so much for coming to this course on our last official day. I look forward to seeing you all in our last unofficial meeting. Yeah, so I'll stop recording. I'll stick around for a couple more minutes in case anyone has any questions.